Can I have sound here? Thank you. Yeah. Yeah, already a plugin. Okay. Maybe I just leave it without sound, I think. Yep. All right. Thanks, Steve. And hi, everyone. I'm Long Pan from Hasso-Plattner Institute. And today I'm going to talk about mutual human actuation. Right, let's start with this example. So this player is having a fully immersive fishing experience in the virtual reality. And you can see he's wearing a head-mounted display. And you can also see how strong he feels the force from the bending of the fishing rod. And in the meanwhile, this player is actually steering the kite in a very stormy weather. And you can actually see how she is struggling against the wind. And this is actually how it actually works. Yep, and we call this concept mutual human actuation. Right, before we dig in, let me briefly explain why we want to do it and what we want to actually achieve. So researchers have dreamed immersion for a very long time since Ivan Sutherland proposed the concept of optimized display back in the 60s. And several challenges have been tackled, such as photorealistic graphics or giving the user's body back. So the next step is to bring the physical feedback as well. And people have tried to build different machines to do it, like the flight simulator here. However, the size and the weight of the machine is proportional to what it actuates. So to provide human scale forces, you will also need human scale machines. So our key idea is to bypass this machinery and by instead just leveraging human power. And we call this human actuation. So in KITE 2014, we presented Haptic Turk, which was the first instance of human actuation. And you can see, instead of a motion platform, here 4 people are lifting the user up and down to match his hang glider experience. And next, in UIST 2015, we extended the concept to real walking VR. Oops, let me play this here. So you can see the player leaning against the cliff walking on the ledge, where in reality, all these are constructed by the 10 human actuators around the player. All right. So from our study in the previous work, the experience for the user was clearly enjoyable. And with regard to human actuator, also enjoyable, but not as much as users. Maybe we should bring it to the same level. So let's make everyone a player, a user. And that's exactly what mutual human action is about. Exchange mechanical actuation between one or more users. And in this way, no one is dedicated to human actuators anymore. So to validate this concept, we implemented a virtual reality system called Mutual Turk. So Mutual Turk approaches it by first offering shared props through which users can exchange forces while obscuring the fact that there's another user on the other side. And also synchronizing the 2 users' timelines such that their way of manipulating the shared prop is consistent across their own virtual world. So let's first talk about our shared prop. So the main purpose of using prop is that it allows users to exchange force without revealing that this force is actually generated by another human, so masking out all the information exchanged between the user. So here are 5 different props that we use in our system. They clearly are not the same, but not just their geometry are different. Each of them actually has different level of expressiveness. So let me take the fishing rod as an example. So the fishing rod you have just seen is the most expressive one because it allows continuous force exchange between the user's hands. And imagine if you don't have this prop in between and just let the user hold each other's hand, they will probably figure that there's another user on the other hand. And that's why we need to have a prop in between. But our fishing rod does more than that, just masking our user's hand. It also masks out the pushing force. So the only information exchange between the user is the orientation and attitude of the pulling force. And because of all this obfuscation, it in the end feels like fishing as you have just seen. And by the way, a small detail here, this is our way to give the instructions to the users in the virtual world. So we just embed the instruction inside of the virtual environment. And here's another one which is less expressive. And with this one, we use the office chair to provide continuous motion. So note that the tank on the cart is now empty. But now it is full because the other player actually sits on the cart. And this user actually feels the other player's weight when he's actually pushing the cart around. All right, and here's another one for impact. And I will just roll the video because it's funnier to just watch. All right, here's another one. And this is a styrofoam board, by the way. All right, and the last one. All right, so you might feel a little bit familiar because it is actually like our TurkDeck before, but this time both are users. So all snippets we have seen so far is what we call action sequences. And this only happens when both users already hold a shared prop. But remember, what we actually are giving it here is one complete story. And each user actually experienced 10 interactions in the world. So we also have to do the transition in between, actually. And let's come to our second part, synchronizing the users. So mutual Turks must not only synchronize the use of the shared prop, but also acquisition and disposal. And the diagram here, by the way, shows the different phases in users' timelines. And let's take fishing versus kite as an example again. So before all this action sequence happens, the fishing user actually has to pick up the fishing rod, hold it still until the other user gets the kite handle, and they can actually start interacting with each other. And after the action sequences, the fishing player has to lower down the fishing rod to let the other player put down the kite handle. But let's just zoom in a little bit more and see what actually happens before the action sequences. So in fact, both users are in their own experiences and are independent from each other. So this is actually the state machine for the fishing user. He can pick up or drop down the fishing rod as he wants. And this is the state machine for the kite user. And these two state machines actually run concurrently until they both actually arrive at the required state. So Mutual Turk uses this concurrent state machine or patrinet to synchronize the users. So we implemented inside of the Unity engine and uses wireless network to do the communication. And the minor detail here, back in time, we used OptiTrack and the Gear VR to do the tracking. But in our demo, actually, we use Vive instead. And the minor detail here, Mutual Turk trigger all the transition in the patrinet or the concurrent state machine, such as a get kite handle event, by using the rigid body information like speed and distance. So like a very simple sensing. All right. So I want to conclude with the benefit of mutual human actuation. So mutual human actuation actually inherits all the benefits from human actuation. Like people are very generic, are very flexible, and also very versatile. But on top of that, mutual human actuation even eliminates the need of dedicated human actuators. But at the same time, it also inherits the limitations from human actuation, like people are slow, not accurate, and so and so. So the only thing different is that designing mutual human actuation experience needs some more extra cares, because basically we have to bring both worlds together. But as you have seen in our video, actually we have pulled out a 20-minute immersive experience out of it, so it's still doable. All right, so I want to keep my talk short, and in the end, I would like to thank my collaborators, Sebastian, and my advisor, Patrick. And I would also like to thank all people that can join in our demo on Monday night. Thank you very much. And on that note, I'm happy to take questions.
Hello, I'm Carla from INRIA. I would just like to hear a little bit on if you have ideas on how to address one of the limitations that you said about human mistakes, like, for example, in the prop where you have like the little steps and the girl is walking on these steps. What if the other human actuator dropping one of those? How do you account for those mistakes?
Yeah, so that all depends on how designer actually design their state machine, like I just mentioned. So the designer actually need to take care what actually the user will have some exceptions. So those exceptions actually need to be dealt inside of that state machine. So if there is an exception happens, the state machine actually should fall back to the previous state, and that the other user actually to do something else. Yeah, like that.
Hi, Huaixu from Cornell. Super awesome talk and work, and I think this is like one of the best work I've been for this year's WIST. So one quick question. I'm just wondering how you transfer from the mutual human interaction to solo interaction. For example, so you have this scene that the people is doing the fishing, right? So I can feel the force from the other people. Imagine if the game is going to the scene that I actually get the fish, so I should feel the fish that's jumping like in my hand, or I can feel the detection from the force from the other side. Like how you translate, like how the transaction happens from the like mutual interaction to like this solo scene. Like, do you have any comments on that?
That's a very good question, actually. So that's why in our system we need to deal with the prop acquisition and disposal. So the user must actually acquire the prop or put down the prop before they actually transit to their own single experience. That's actually how we do it. Yeah.
Okay, so I'll ask another question, and that's that in addition to accidents, There simply are things that happen when you have people in very close proximity. And I noticed that you have them, certainly in the imagery, really, really close to each other. So if a person is picking up a stool and putting it down, the possibility that they might have part of their hand pass over what they see as being an empty thing, which actually has a person standing over it. It would seem to me that that really could happen. Did that happen during your studies, people bumping into each other literally? And if it did, how do you deal with it? And if it didn't, it will happen, so how do you deal with it?
So that's a very good question. So right now we don't really have like a very good solution for that, because it's like a very generic VR problem right now, because we basically just cannot avoid all the exceptions. For example, if the player actually can leave out the tracking space, right? We have no full control of the player. So right now, what we actually implemented in our system is like what the Vive system actually does is to reveal the chaperone around the player to remind them actually there's some other things in the real world. But I think that's a very good question to solve, and actually, I think many people are actually working on that right now. Yeah.
So one suggestion, and that's that while you might actually reveal that there's a player there, right? Why not make it part of the scenario? So if you bump into the other player while you're fishing, for example, maybe it's, as you look down, you see this fish that leaped out of the water, or a moose came, or something happened that would fit the scenario.
Yeah.
And you have full body mocap, so you might actually be able to make some predictions about when those collisions will happen. You certainly would know when the collision actually happened.
I see. That's a very good idea. Thanks.
Anybody else? No more questions? Okay, in that case, thank you very much. Thank all the speakers.